we start from the beginning, being, well, sound a little bit faster, and arrive to these three principles, the one that I told last time. So there are several steps in computing. Well, we need to arrive to the Lebesgue integral in order to compute well, what is an integral of a very rough function. And so the first thing is the Lebesgue measure, no? So what is a measure and what is the Lebesgue measure? So let's say up to now, what we know. If you remember the scheme, the Lebesgue measure is built by, well, we know how to give measure to a union of these joint intervals. And that gives the outer measure, because you take the infimum, you give me any set, you just find the infimum of the measure of open sets which contain that set. That's it. The Lebesgue measure is n, and so then we have the Lebesgue sigma algebra, because well, once we have the outer measure, we can build the Lebesgue sigma algebra. So which is L. And what we know is that, well, up to now everything is formal. It's a little bit formal, because the only thing we know is to compute M star. And then we know that for some set, well, M star is satisfies the property of the sigma DTP, so, or like say the exclusion property, you know, that we can split any set into two parts, and the sum of the other measures is of these two sets is equal to the measure of the set. No, you remember that everything is form is a line. You define, you have, so you can give numbers to any set, a number which is the outer measure, and then for some set, this number is additive. Okay? So if you join two sets, well, actually it's a little bit more subtle, but in any case, you can think that the idea is that if I have a set, if I cut into half, it's simply the sum of the two pieces. So far it's formal, and then you show that it is the set for which you can do this excision property is a sigma algebra. So, well, it's an algebra, because essentially, certainly you require that if you have two disjoint sets, the measure of the union should be the sum of the measure. So you need that the sets to which you can give, well, which behaves nicely, should be an algebra. No? You can close it, and then, well, if you give a measure to this guy, you have the measure of the opposite. So this is an algebra. And, well, but a little bit more. So it's always closed under countably many operations. That's why the sigma algebra. And the important thing is, well, you ask if this is a little bit more than the trivial sigma algebra. You remember we have an example for which you start with an outer measure, and then you show that essentially this sigma algebra is the trivial one. There's only sets of measure 0 or sets of full measure. And then it means, well, essentially, it's like the light is. So I'm on or off. There is nothing else in between. Okay, so the important thing is that this sigma algebra contains the Borel sigma algebra, and now we are much better, in better shape, because the Borel sigma algebra is a large sigma algebra, because it contains the open sets. Then we know it contains also the complements, so the closed sets, and then the union, countable union of closed sets, and the countable intersection of open sets. And then, well, you can iterate the procedure up to proving that this sigma algebra, well, has a cardinality which is, well, which is not, well, it has a lot of sets, so the cardinality is above is not countable, certainly. So it contains a lot of sets, even not only the open set. And now we have the first regularity. So you ask, how much is larger? Well, so you know for sure that So if you give a set E, which is in L, then E, so there exists, let's say, a G delta set, which is an intersection, such that the measure, well, okay, let's say G delta, which is equal to E union N, and the measure of N is equal to 0. So essentially, the sets in the sigma, from the point of view of the measure, every set is basically a G delta set. So this is the first regularity. Well, and then you have the complementary regularity, that is, well, you can take an F sigma set, which has the same measure. So from outside or from inside, simply because you take the complement. Okay, so this is the first regularity. So essentially for the measure, everything is a G delta, and essentially, well, if the set has finite measure, well, not only, we don't need a finite measure, but let's say, essentially it is an open set. So here there are three pieces. The first is the measure, the two sigma algebras, their difference are just the set of measures 0, and this is quite large. But actually for the measure is not too large. It's not too large. Okay, so this is the first thing. And then we are very happy because now we know a set functional which satisfies this problem. So, so now the next part is well, we have really to, well, there are some regularity theorems. You want me to also cite these theorems? The most important one is essentially that, so the most important, for which you can recover everything. And actually it's the definition of this, is that the measure of the union of these joint sets is the sum of the measure, which is in the definition. But actually this is the continuity of the measure in some sense. It's continuous with respect to the operation of the algebra. So the second part is the Lebesgue integral, the Lebesgue, let's say, measurable function.
Excuse me, but continuity of the measure as a function, as topological spaces notion, or
Is
continuity here refers to the notion of continuity in topological spaces, or
because in very theoretic measure theory, you don't have any space, but you have only the algebra, and then the countable union, it gives you something like. Well, I don't remember very well. I studied years ago. So it's something like some topology-like structure, and then the sigma additivity is the continuity of the function. But I have to check. This was what I remember. Well, it's a little bit advanced here, because everything is formal. You don't have any. So here the space is R. I'm not writing R anywhere because the line of reasoning is the same for any measure. But in any case, we always have, at the end we have R to D. This is the most complicated space we have, but actually everything works if you are in a separable metric space. If you want to understand why this is continuous, is everything is formal. You have only the algebra of set as a function of n, and then the continuity means exactly the same. I had to check, we didn't check. So measurable function. So the measurable function is the two. So we have to understand why I give the construction here. Remember that the idea is that if I have an integral, instead of seeing vertically, the strip vertical, the vertical strip, I just see as a sum of horizontal strips. And so now I have to define what is the measure of the counter image of intervals. But I have to require that the counter image of integrals is a set to which I can give a measure. No? So the picture to keep in mind in all these constructs is that, well, at the end I have to compute what is the integral here. No? That's the final goal. And so for the Riemann, remember I just do the vertical strip for the leg. Essentially I imagine as a sum of these slices. Okay. So I have the first slice, the second slice, sorry, this one is not here, and then the third slice, which is the sum of these two pieces, and that's it. So basically, I have to, and the measure of this slice, if you imagine they're small, thinner, essentially is this size times this measure. And so I need to give, so the counter image of this interval should be essentially something that belongs to this algebra. Otherwise, well, so you can compute an integral using the outer measure. But the main problem is that, well, you don't have the properties of the integral. For example, if you have two disjoint sets, you want that the integral on the reunion is equal to the integral in the first plus the integral in the second. No. So I can certainly give a formula for a general function using the outer measure. But the problem is that I'm missing the linearity of the integral, and I'm missing even more. I cannot pass to the limit, I cannot do many computations because the properties, I have to keep some properties. So from this one, essentially you say that f to the minus 1 of any open set belongs to the sigma algebra. Okay, so this is very close to the construction of M in some sense. So I need a property and then I assume this property. So here I need that they are additive when I cut the set into two parts. And here I need that the counter image of any open set should be something to which I can give a measure. And should be one of the good sets. So how many F? Because I have a problem now. I can have just one F. A priori, only the constants, for example. But actually, if the sigma algebra is like the empty set and the whole line, the only measurable functions are constants. Because the counter image of any open set can either be empty or be the whole set. And now there is only a family of functions, one-dimensional family of functions, the constants. So you see that a priori I could have very few functions. But you discover that if f, so L is the symbol for measurable function. Sorry, L0, this is my mistake. No, this is L, and the measurable functions are called L0, usually in the literature. So the 0 means that you don't require any integrability property. If you put an exponent here, it means that once we know how to compute the integral, for example, if you put 2, means that the integral of f squared is less than plus infinity. Here do not require anything, so you would put the exponent 0 there, in some formally, but clearly you cannot. But the meaning is that you don't require any integrability, just measurability. So now you decode it. If f is continuous, then f is in L0. So at least the continuous function is fine. Then you discover something more, because that if fn converges to f pointwise, then fn is in L0, So it's closed for pointwise limits. So see now we are enlarging and enlarging the sets. At the end, we arrive to something that, well, essentially you cannot exit from. If you start from a continuous function, you cannot exit. And okay, what was the? There was another thing that I want to compute. No, that's it. So essentially, these are the two tools you use. Okay, so let's do an example here to show that we are very nice, in a very nice set. So you know what is the Riemann integral? So when a function is Riemann integrable, yeah. I don't want to. I don't want to arrive to the theorem. This is a consequence of the fact that you take the upper and the lower sum and the distance should be the same. So essentially, if I have a function, using this continuous one, well, then I take a partition here. The partition, well, what I control is just the size, no? Actually, if I smart, I take the partition exactly. This point should correspond to that point. And what I do is that now I approximate the integral with two integrals, two sums, finite sums. So first I take the lower. Yes. And then I take the upper. And this one is here, and this is okay. So f is Riemann integrable if, well, f is between, let's say, two functions, let's say phi xi minus xi plus, and these functions are simple functions, step functions, sorry, step. And the two integral converges. Okay, we don't need this part here, but let's say we call that okay, the Riemann integral of xi minus xi plus xi minus less than epsilon. For all epsilon, I can choose if for all epsilon there exists this. Okay, so let's prove that fact. So from this guy over here, this means that f is the pointwise limit. Actually, it is sometimes a uniform limit of well, pointwise limit, but certainly is a pointwise limit of step functions up to a set of measures. Step functions are certainly measurable. So I deduce that Riemann integrable functions are certainly Lebesgue measurable. So I'm very happy because, well, certainly can compute, well, we'll see later, the integral of functions which can be computed earlier. Otherwise, it would not be an extension. Okay. So let's see now so I want to say that the regularity over there, how it translates into regularity over here. This is the second regularity principle. So, and the important thing, the most important is this part here, no? So every time I have to prove something is measurable, essentially it is the limit of, but actually we know that everything you can construct will be measurable if we don't use the axiom of choice. So the second regularity. The second regularity is very close to the first one. So the philosophy is that here we are working on open sets, essentially, up to a set of arbitrarily small measures. Now you see, this tells me that essentially every function is the limit of continuous function. It's not said like this, but more or less. Because what you can construct, actually, I mean, really construct. Essentially, you can construct polynomials. If you give me sums, I can construct analytic functions. And then, well, and then I'm starting being in trouble a little bit, not formally if I compute. Well, but they construct step functions, and they construct simple functions. So let's say, remember the definition here. Phi simple is a sum finite of some constant. It is simple. So I can build a limit of simple functions, limit of continuous functions, and then it's starting a little bit. Really, I don't have any, I cannot imagine another way of doing that, of doing more than this. So let's see even the simple function. The simple function, if you use that, you can have a, so let's make another example. So give me a set E. Let's say the measure of E, well, it doesn't matter, but let's say less than +infinity, just to make something thinking easier. So find open, let's say G, closed F, and F is contained in E, contained in G, and the measure of G minus F is less than epsilon. Can I do that? Yeah, because it's the first regularity. The first regularity gives me G, and the complement gives me F. Okay? Then let phi, let's say psi is a continuous such that psi is between 0 and 1, and psi is equal, let's say psi on F is equal to 1, psi on R minus G is equal to 0. Can I find a function like that? Let's make a drawing. Also in RD, doesn't matter. So let's say this is F. And this is R, or the set at G complement.
Yes, because that's like partition of unity, just we take something decreasing in between the two things.
So R is a very nice topological space. Give me two closed sets. There exists a continuous function. To this joint closed set, there exists a continuous function which is 0 on 1.
And also because here we are working with this set is of measure less than infinity, so we can bound it by a closed interval, and the theorem says there is
no, measure less than infinity you cannot bound by a closed interval.
Isn't it, if a set is of measure 0, is it bounded?
Measure 0? No.
Sorry, it measure less than infinity.
No.
Ah.
2 to the minus pi.
Yeah. But if the measure is less than infinity and not zero, it must be bounded, right?
If the measure is less than infinity, but?
And not zero.
No.
Ah, okay, yes.
Which I can split.
Yes, sure.
But R is very nice.
Yes.
Yes, this I think is the fourth separation property. One of the latest. Not the third, I think it's the fourth. Given me to close the disjoint set, there exists a continuous function which is 0 on 1 and 1 on the first. Okay? So now let's see how much the function phi is different than xi. So the function of e minus phi is different than 0 on, well, on f they coincide, on the complement of g they coincide, so it's g minus f. So let's recap this example. Give me a measurable set, there exists a continuous function such that the set where they differ has measure less than epsilon. So when I say limits of simple functions, I'm not saying much more than limit of continuous function. Because this is I remove a small arbitrarily small set is continuous. Indeed, actually, we don't. At the end, we work a lot, but we never exit too much from polynomials, unfortunately. Even the computer, when you have the exponent, the computer computes not the real values, just the series. Okay, so, and now, after this example, can you state what, or I'm sorry. Yeah, can you state what would be a second, or actually would be the third, because we saw first another regularities. So the second and the third regularities.
Excuse me, but before this, here in this discussion, what do you mean is that the difference between continuous functions, the limit of continuous functions and the limit of these simple functions is not a big thing, because just we can approximate these with a continuous function such that the difference is this. Is this the, okay.
Yes. It's not, you don't gain anything.
Yeah.
Really everything is the limit of continuous, or everything the limit of simple, whatever you prefer. Simple actually is nicer to use, because you don't have to care about these small sets, but actually you're not, like here, you're not really, well, you're exiting because essentially, so the philosophy, you prove that all the bad parts, they go to some small sets. And also here, all the discontinuities, they are in some small sets, essentially. And so, if you give me f, which is measurable, essentially is something which is continuing up to a small set. So all the bad parts will go into a small set. But the small sets, they can be very complicated. But actually, they have a small measure, so you don't care. So this is more or less the philosophy. So now, let's take the example. The example tells you that actually also this is continuous, also this is continuous. So let's take what you think they can be the two principles, starting from this one. This one says that opens, that measurables are basically open. So and actually let me restate this thing. So this is for every G, for every E in L, for all epsilon there exists O open E contained in O, and the measure of O minus E is less than epsilon. Okay, so let's say the second or the third, whatever. So remember, the second is that, well, it's already written here. A simple function is basically continued up to a small set. And the other thing is that we are using the pointwise convergence. So essentially now, you just translate back this if you just wanted to work with continuous functions. So what would be the third principle? Or one of the two, just up to you. So the philosophy is I have to replace all the statements here. I mean, the function is measurable and the pointwise convergence into something which essentially, as I just work with the space of continuous functions. And then I have to add set of measures or small measures.
So the short functions are continuous, basically have to measure two sets of measures here.
Okay.
Continuity as
Yeah.
well.
So this F is in a 0 for all epsilon. There exists phi, set of xi C0 of R, such that the measure of the set where F is different than xi is less than epsilon. So it's exactly this guy here. And this is the losing theorem. It's a very important theorem. Second is, well, if the functions are continuous and I want to get a continuous limit, I have to require that, well, it's a theorem, no?
Diego? Diego?
Yeah, this is Egorov theorem. So this is the name of this guy is Egorov. Sometimes it's written with a V, not with the double F. The books write with double F. I usually write with a V, since it is Russian. You have some freedom. I never understood if they follow some rule in translating the Russian F, or Russian. So what would be? So now I replace this guy. I want to replace this guy. But we saw as Friday, that maybe for the others.
So is this a sequence of simple functions?
Well, or just a sequence of function converges to if a simple function converges pointwise. Which means for any x, fixed x, the limit converges on a set E. And here I need an assumption. M of E less than infinity.
Then if it's measurable set for.
Okay, now I need to speak about so what is the convergence for C0 function? For continuous function, what is the notion of convergence which works?
Uniform for integral.
The uniform. So the statement would be then Fn converges to F uniformly. And this is an L0 naturally, otherwise I cannot work. And okay, but this cannot be true.
On a smaller set of
Okay.
measure 0.
On K or F, doesn't matter. Actually, here I can take a compact set. K compact, it's better because the uniform convergence for compact sets. The uniform convergence in R is a notion which is a little bit. You don't like that.
The tricky part for me is that we prove that it's for closed, and we know that bounded measure is not implied bounded sense.
No, yeah, but since it is the sum of pieces, at some point the remaining part going to plus infinity has more measure, because otherwise it's always a sum from which it diverges. There is this on with the measure
E minus K.
so K on K contained in E and the measure of E minus k less than epsilon. For all epsilon, then this holds. So for all epsilon, there exists k such that this holds. Okay. Are you fine with these three principles? So maybe let me see, maybe okay, let's do some exercises and then maybe we go to the book. So we keep the examples. So, sorry, we keep the regularities. This is not needed. So, for example, so here I say, so let's try this guy. So I ask, for every E, there exists K compact, K contained in E, and the measure of A minus K less than epsilon. So for all E, for all epsilon. Sorry, for all epsilon, so let's say given E like this. For all epsilon, there exists a K which depends on E and epsilon, such that this holds. Okay, what the regularity states?
Can we take the indicator function and apply the third regularity to
Which one? The first, you use this guy?
No, I mean we have the set E, so we can take the indicator function on E,
Yeah.
and it would be
F
measurable.
psi is equal to 1 on a set of measures, or on a closed set.
No,
Here? Or here? There is no limit. Which one? This one? Either this one or this one.
no. In fact, I was thinking of applying the second one, but I need some sequence of functions, so I was going to define it.
There is only, I give E, I don't see any sequence.
Yeah, but I can take the indicator function of this this set
Yeah?
and but I'm
Yeah, listen to it. True or false? So, the regularity, what does the regularity say? For all E, okay, essentially there exists F. So if I take E, so apply to E complement the first regularity. So this means that there exists a G such that E complement is contained in G and the measure of G minus E complement is less than epsilon. And then let F G complement closed and the measure of E minus F is less than epsilon. Okay, so this is directly from that. So I have a closed set inside which measure is less than epsilon. Now, I need a compact set. So F is closed, so let Kn minus n intersection f. This is compact. So the question is Kn essentially encompassing all the compact sets that I need here or not? So if I take a compact set contained in E, certain at some point is contained into this guy. And you see F, so this is pretty fine because F is already basically my set. So if I want to measure F with compact sets, essentially these Kn are all the compact sets I need. Take limit is not compact.
But F is.
Okay, so let's give an example. F is equal to the union over I in n, I plus 0, 1 half. Or let's say I plus 1 half. Is F closed? Yes or no? Are you convinced?
The complement is the intersection of
The complement is the union of the open intervals I plus 1 half, I plus 1. So that is closed. Any doubt here? Okay. So this is closed. And now, so what is the measure of F?
Infinity.
Yeah. What is the measure of any compact set? Could be plus infinity, the measure of.
No, because it's sum of finite intervals.
Some point is contained as bounded interval. Okay. So can I approximate F? So there exists a compact set which approximates F with a small measure, up to a set of small measure.
No.
No, why? Who said no?
Yeah, I simply no, because if so, then the remaining part,
Yeah.
because
The measure of E is
F,
yeah,
the measure of
exactly.
F is infinity, so if I take a smaller set, it would also need to go to infinity.
Exactly. Otherwise, if this is Z, it should be n plus epsilon. So if there exists a compact such that I add the measure of size epsilon and I get the measure of F, the compact is bounded, no? Any bound set plus epsilon is bounded. So for all compact, the measure of F minus K is present. Okay, so we have the answer here. So the answer is yes or no?
We also assume that the measure of E is less than infinity.
No. So the answer is
No, but I mean, what if we add this condition that
yeah, this is the second part. So no if the measure of E is less than infinity. So now let's come back here. So now measure of F, so measure of F or of the set F is less than plus infinity. So what I can write? F is certainly the union over n of Kn. Do you agree? Okay, and now what we use? You remember I canceled the fundamental property here
The continuity.
of the measure. You see how the tricks enter, no? Because now measure of E, measure of F, then is the limit over n of the measure of Kn. And now the trick works because if this is less than plus infinity, the definition of limit means that one of those is equal to this guy minus epsilon, or larger than this guy minus epsilon. So there exists Kn such that the measure of Kn is larger than the measure of F minus epsilon. So there exists a compact set. So now let's apply to this procedure for this Kn. The measure of E minus Kn is less than, okay, I have an epsilon here, so 2 epsilon. So yes, if okay, very important exercise. Sets of finite measure are essentially bounded.
Or what?
Essentially bounded. Essentially means, well, you will see that also is almost everywhere. So up to a set of Morse measure, essentially whatever. These are just means that you always remove set of measure 0 of set of arbitrary small measure. So the statement actually is that one. So the statement in this case essentially means if you let me to remove a set of arbitrarily small measure, then or small measure, then the set is bound. Okay? Question over here? So this is one of another regularity in some sense, no? Is another additional regularity that is used here. So that's why it appears to be compact. Now you see why I need this assumption. Otherwise it should be a closed set, unbounded closed set, but it's not true that if the limit of a continuous function on an unbounded set is continuous, then the convergence is uniform. That's the problem. Indeed, this is the second point. So we discovered that the first regularity is sharp, as it's written here, can be only improved by an inner regularity using, well, you have the outer, you have the inner, certainly taking the closed set, but to move to a compact set, you need to require this guy. So let's add this comment, remark. So for all E, there exists F. For all E, for all epsilon, there exists F closed, F contained in E, and the measure of E minus F less than plus infinity. If measure of E less than plus infinity, F can be compact.
Excuse me, this should be less than epsilon. Measure E minus F.
Because I was thinking already to write this guy. Okay, so this is the addendum. Now let's work a little bit about this guy. Are you fine with this bit? This is, so let's work a little bit about this guy. So first of all, well, I know that the compact set, it comes out naturally because of this assumption and because of that remark. But certainly I may wonder if it's not the case too. I mean, if there is this another proof which removes this assumption, no? So let's take f is equal to, I can give something explicitly, for example, the hyperbolic tangent of x plus n. Okay, it's not in, this is just to be something explicit, but let's say this is in x, let's say f plus n, doesn't matter. So this is minus n, and the function is like this. It's not really important which function. The important thing is that it's just the translation. Okay. Is f converging pointwise?
Yes, to the constant function.
Yeah. Is fn converging uniformly? No, because the distance is always 2, no? The norm C0, you know what is this norm? You know this symbol is the max, the supreme, yeah, because it's not a compact set. The problem is really that it's always true, so no uniform convergence. On the other hand, is the limit, so this is equal to f, is C0. So now you see that essentially you can have function converging pointwise whose limit is continuous, but you don't have uniform convergence on a large set, no? Because actually fn minus f, when this guy is less than 1, this measures classicity. There is no way to remove everything. And the problem is the fact that, well, you can see also the fact that the topology for continuous function in R, the uniform topology is not the next topology. It's not the natural topology. On compact set, yes, it is the natural topology. Agree. Okay, so there is no way. I think then now we need only to prove the third or see the second. So I think we construct now the proof of the second one. We do it again. Yeah, that's right. We can choose actually. Up to now, we can also prove the third. They can be exchanged in some sense. So proof of Agerov. So how to build it? The idea is so let me write on the two sides the pieces that I want, and then I try to merge. So the first one is the for any x. So for all epsilon x, there exists n which depend on x, let's say n of x, such that for all n greater than n of x, fn minus f is less than epsilon. This is the assumption. This pointwise convergence. On the other hand, I need the uniform. The uniform is that for all epsilon, there exists, let's say, m, so x epsilon here. M, which depends only on epsilon, for all n greater than m epsilon, for all x into this subset. Sorry, I did the same mistake as before, because I have epsilon there and this is another parameter. So if you allow me to call it delta, otherwise really in my mind they are different epsilons, but on the blackboard they are the same. Yes, okay. And then you have fn minus f point x for all x there is less than delta. Okay, so this is the goal and this is the starting point. Okay, so now you know that for taking something very large, so if I fix delta and I take n very large, well, the number of x such that this satisfies is going to increase. No? So I want to get it right because it's standard to get some mistake. Then I have to restart. Which one? Okay. So the starting point is to define the set which is delta and k. So these are the point x such that this holds where here I replace an x by k. So for all n larger than k, fn of x minus f of x is less than delta. Okay. So essentially I say, well, you fix me k, so this is equivalent to say that n of x at delta is greater than k. Sorry, less or equal, less or equal, because n should, no, greater, there should be n greater than equal. So, yes. Because this implies if this
No.
is,
Because if
it's the opposite. if this is satisfies, then it's larger than this guy. Yes, okay. So it's just, I measure the set, or at the end I measure this set. So now, what happened when I let k go into plus infinity?
Becomes C. For convergence.
So any point when k is very large, since for any point I have this function and x delta, delta is fixed, this is going to increase up to the whole set.
E.
Becomes
Is
C
equal
because
to-
point convergence.
Yeah, exactly. The whole E. And now, regularity over there. So the other, well, basically the fundamental property from which you deduce everything. Which implies that the measure of E is the limit over K of the measure of E delta K. You see where the property, I told you that's the fundamental property, and it enters in every proof.
because the
Because
sequence EK increase,
increasing sequence is
Yeah. Because if this condition, if it holds for 1x with a given k, for k plus 1 is still whole. Just k is increasing. Otherwise, the other one was 4. So now, So far we haven't used any property of the finite of the measure, no?
Yeah.
So, but now we can use it. Because we can say that, well, E has finite measure, so there exists. So for all delta, this holds for any fixed delta. No. There exists a K, which depends on K of delta, such that the measure of E delta K of delta is larger than the measure of E minus, okay, here I can fix whatever I want, but essentially any alpha, with alpha greater than 0. So for any alpha, if I fix alpha, then I take alpha, I can find a function such that this guy holds. So it just telling me that because of the finite measure of this guy, they are almost all E. You see, if this has no finite measure, this may happen as in the example, and clearly the measure is going to converge. Actually, it will be plus infinity, but you don't get this inequality because it will be plus infinity larger than plus infinity. It's a nonsense. Final trick. So the final trick is difficult to appreciate, I understand, but actually is the fundamental thing. Another fundamental thing, which is not really there.
But also, because of this condition, we are also, it is true only because this sequence EK delta is increasing. I mean, just...
Yeah, otherwise would be the U. Yes. But I already used this here.
I mean, only that the measure of E is less than infinity doesn't give us this expression. Only because...
But if you use this guy, yes.
Yeah, I mean, if we know that the measure of ME is less than infinity, but we don't know, assuming that we don't know that EK delta is not increasing.
No, then well, but if you have the limit, is the definition of the limit. Why? The E delta K is contained in E, and then if this holds the limit, by definition, the measure is the monotone, so this is for sure.
Yeah.
What you cannot write is this limit if it is not increasing. Because this guy means only that E is the sum. But since it is increasing, the sum is the limit of the partial sum. The partial sum is the last one. Yeah, you use here is increasing with K. Yeah, it's in this part. Once you have the limit, this is just the definition. So now the trick is that this is, you see, you're using countably many alpha. And uncountably many alpha, any alpha. You're using any delta. So, last step, pass to countably many. So, in particular, now, you see, for any delta, so I take delta equal 2 to the minus I, alpha equal epsilon 2 to the minus I. There exists Ki, because now depends on the index, no? Now everything depends on I, so I, this guy I can say it's I. And this is a delta alpha, actually, because I fixed that. Such that the measure of E, and now I have 2 to the minus I, Ki is larger than the measure of E minus epsilon 2 to the minus I. Okay, let's make a drawing. So let's say this is E. Sorry, let's say I need to cancel the first regularity. And also this guy is not important. So let's say this is E. And what I said, let's look here. you give me delta. Okay. I find that delta is larger than 2 to the minus I for some I. Okay. Then I choose ki such that this guy satisfies this condition. So inside this guy are the points such that if I give m delta larger than ki, this holds. So let's repeat. So you give me delta, I find 2 to the minus I. From delta, I say 2 to the minus I, 2 to the minus I is less than delta. From this guy, I found the ki. So if m is the m over here is larger than ki, then let's come back. Then I'm inside this set. And if I'm inside this set, I go here, it tells me that Fn is less than delta, which is 2 to the minus I. Then on E 2 to the minus I ki, F n x fx less than delta, so 2 to the minus I, which is less than delta, if n is greater or equal than m delta, which is greater than ki. Just I could write the last passage, but actually I prefer to make a picture to understand why. So give me delta. I say m delta equal to ki. What happened on the set E2 to the minus I ki? Well, it means exactly that n larger than ki, which is my n delta, their difference is less than 2 to the minus I. This is the definition. So here is okay if km delta m 2 to the minus I or m delta is larger than ki. I just constructed the set for which essentially I'm saying you give me delta, I find a very large index, and I give you a set for which the condition, the uniform condition holds for this choice of delta and delta. So you see, I just saying essentially this is m delta is a function of delta. I'm saying on that set the function, if I give you delta, the value is given by this ki. Okay. How to end the proof?
Just because now if we sum.
Exactly, is the intersection. You give another ej, so it's slightly different. Let's say this is e 2 to the minus I ki, this is e 2 to the minus a kj. This is good for k larger than 2 to the minus j, when I give the value m delta equal to kj. So let's compute. So let's call f. Actually, I can take e closed, no? But it's not important. So let's say f I don't like. Let's say that G is open. Let's say H is the intersection of an I of this set. And K contained in H compact with the measure of K or H minus K less than epsilon. Now the epsilon is the epsilon here. These are really the epsilon in the Okay, so let's see if K is the right set. On K, I have to prove this statement. So I give you delta. What is the value of M delta in the intersection?
The smallest KR.
Yeah, look here. You give me delta. I find the I such that it is whole. I find the Ki. I set M delta equal to Ki. Then this is a subset. H is contained here, or K is contained here. And so it holds that this is less than 2 to the minus I, which is less than delta. So in the intersection, I'm exhibiting explicitly the function M delta as a function of delta. It is a step function. When delta is between 2 to the minus I, 2 to the minus I, 2 to the minus I plus 1, I give the M delta is the Ki. Just explicitly, I construct the function. Okay, so essentially I do the following. Here I have delta. This is M delta. So 1/2, 2 to the minus I, 2 to the minus I plus 1, and here the value is this Ki. And intersection, by the definition of E and 2 to the minus I, Ki, the estimate is correct. So this condition is correct. So the last step is to prove that what I'm throwing out something, what I throw out, what I trash is something that is small, arbitrarily small. So I'm almost recycling everything. Why is that so? So what I'm throwing out here?
We are throwing out E minus K, which is less than E minus H. Therefore, we sum over epsilon to the power minus I, and the sum is over I, so it is less than
2 epsilon. Do you agree? So what I'm throwing out, what is the rest here? Actually, I have a K, which is, let's say, a compact set. What I'm throwing out here? I'm throwing out 2 parts. Here is H minus K, and then E minus H. What is the measure of H minus K? It's already written here. What is the measure of this guy? It's the measure of E minus the intersection of this E 2 to the minus I, Ki. Okay? By definition. So this is, okay, the measure is less or equal than the sum. So the worst case is when essentially the complement sets are all disjoints. Otherwise it's even better. So it's the measure of the union of this guy. So this, because this should be the union of E minus E to the minus IK, and this is less than the sum. So the E minus E to the minus I, Ki. And this is less than sum over I, epsilon 2 to the minus I, which is epsilon. Okay. I throw out 2 epsilon, and I have something which is uniform convergent.
I have just one question. Where did we use that these fn's are in fact measurable? Because it's a statement of the theorem.
Otherwise, you are in trouble in measurability. Otherwise, you have that something small and you don't know what to say. And you, well, also in that computation. Okay, are you fine? So essentially, this is really used a lot of time. Okay, so So let's prove now that we have the second part, losing.
What?
Let's prove the third, losing.
Use
you are
the
fine.
second one?
The second one is Egorov.
Yeah.
What is the notation of Littlewood? So the third one is the losing. So essentially any function is essentially continuous. So let's cancel. And now, so you see the steps here is just that you write the condition of the pointwise convergence, and then well, you work a little bit in order to show that you are throwing out almost nothing. Okay. So let's put some hint here. Do you have any hint? So we know Egorov.
Oh,
We know that we can
almost
approximate.
averages, almost averages. It's mean almost averages. So we can use definition of almost averages, for example.
We can approximate if by step functions or
Yeah,
Yeah.
that was one of the properties.
Yeah.
So let's say first we know that this f is in L0 and
Then
let's say I always assume less than is bounded. You don't have sets where it is plus infinity. So it's always assume values in R. There exist phi simple such that well, actually what I know is f in 0 bounded such that phi psi simple such that
They converge to f pointwise.
yes, phi less than f less than psi and psi minus phi less than psi.
Yeah.
And phi they are bounded. Yeah, this is certainly this is a starting point because at least I have a sequence. But then I have a trouble which is boundedness, and then we'll treat later. And then we have that these are not continuous. This is the worst part.
Yeah. But they are still measured.
They are measurable, yes.
Yeah, but so by growth theorem, we can throw out a small set and they become uniformly convergent.
Yeah. But I need this assumption.
Yes.
Then I put for any minus n, phi converge, there exists a compact set which are contained in minus n, and let's say the measure of, let's say, minus n is minus kn is less than epsilon. Well, we see that epsilon have to be chosen. And then what I have is that phi converges to F uniform.
But also we can use the same we discussed earlier in the literature that if we have such a simple function, we can find a continuous one such that the measure of the set where they differ is smaller than epsilon.
Yeah, and this is the last part. Yeah, and so phi for all epsilon, there exists a psi continuous. Let's say this is phi n. Phi n, sorry, the set where the measure of the set psi n is less than, well, here I have several epsilon, let's say epsilon times psi second, because then I have really, I have I have a lot of epsilon, so I have to match a little bit, no? But yeah, these are the three ingredients.
So now we start with the simple functions, And for every one of these, we get the continuous one, and the difference is at most 2 epsilon.
Oh, so we start with the simple function. Sorry, can you repeat it? I wanted to say something that
We are given an f.
Mhm.
So we get two simple functions, phi and psi. Yes.
and you have bounded here, bounded here. You have to treat a little bit these two parts.
Yeah, we are assuming now that f is bounded, right?
But it's not yet.
Not what?
I'm not
Yes,
saying that F
here
is bounded.
for every
And I'm not saying that the set is bound.
So if it is not bounded, we can the place where it is not bounded is of measure small one.
Where is large?
Yes.
Yeah, okay. So first step, no, that's false. That's false. Can be plus infinity. Because you are saying that this set converges to converges to the empty set. But if you remember the proof, you can only prove that if you have a family of decreasing sets and they have finite measure, the measure of the limit is the limit of the measures. Okay, so but it's true. These are the 3 invariants. So now they are just technical points.
Okay.
Just technical.
If it's not bounded, I can take a sequence of bounded functions converging to f, right? And I apply the theorem for every bounded one.
But still, you can't say that when they are different as more measure. They apply, even they are continuous. But the set where they are different as measure plus infinity. Because you are using the following fact. You have a family of sets, decreasing family of sets. The limit is the empty set, which just measures 0. You can say that the limit of the measure will be 0 only if one of them is bound. That's bounded measure. Otherwise, it's false. Just taking the translating half line. So this is the first trick. So assume that you can prove the theorem in any bounded interval. Okay. Then it's true that it holds for all R. So assume that for all, let's say, minus n, there exists phi n, let's say psi n, and the n is here continuous, and kn contained is minus n, and f is equal to psi n on kn. Drawing. So let's say minus n, let's say n and n, doesn't matter. Well, it's equal, it's the same. So for all interval, I have a compact set larger. Let's say the measure of minus n minus kn is less than, okay, I'm smart, epsilon 2 to the minus n, because I'm going to do this thing. So here, essentially, the function is continuous. So essentially, if I take something larger, I have another compact set. I add some pieces here, and it is continuous. Okay, so essentially, if I take, you see from this guy that essentially there exists, I left it as an exercise, this one, exercise. There exists f closed, the measure of r minus f is less than epsilon, yes. And f restricted to f is equal to some psi and psi, well, is continuous on f. This is an exercise, just the fact that essentially from this guy you see that what I'm moving, if I take the intersection in any set, I'm not removing in the whole line, I'm not removing more than epsilon. So psi can be extended to a continuous function of on R, because the trouble is that these psi n are continuous outside, but I'm not saying they so for another choice this is outside. Only on these sets the value is fixed, so certainly they converge. So to some point which is continuous on F. Well, yes. I just take, for this, the union is an open set. R minus F is a countable union over J of some intervals. And, well, extend psi, well, in any way to be continuous on those intervals. So for example, if this is the interval, these are the two limits value, I can take this one. This is any continuous extensions. So this is the way to manage the fact that the support of F is unbounded. And this is the only trouble. Because whenever I'm bounded, I'm a set of finite measure, and now I can use what you say. Okay, maybe let's stop here. Maybe we will see the exercise later if you don't understand. But actually, this is a fundamental tool. It's always the same trick. So the idea is that, well, if every time I throw out something small, arbitrarily small, and then I sum up, I'm throwing out something which is still small. Okay? So the conclusion here is that F, we need only to prove losing in bounded sets. Stop here because we started, actually that block is not up yet. So, okay, so see you Friday and we finish the proof.